So our next speaker is Michael Foss-Feig. He's going to tell us about proving critical states of matter on a quantum computer.
Okay, thank you. So it's a real pleasure to be here, and I appreciate the organizers putting on such a nice conference. I think everybody should probably email Michael Collins about once a day until he agrees to keep it in Telluride for the foreseeable future. He said that's the question. So the talk today, it's going to have two parts. I'm going to talk a little bit about our hardware and some developments on our hardware. And then I'm going to transition into telling you about some work that was actually done on a previous generation of our hardware that I didn't talk about. So it's a little unfair, but to be fair, they're very similar in the way they work. It's just that one has some technical improvements, and I kind of feel obligated to tell you about the testing that we're doing currently. And this work is work done primarily by Reza, shown here, and then the other people listed out here, with an emphasis on a large number of people on the experimental team who actually sort of, design, help sort of build and operate the system and take the data. So this is a picture of our most recent quantum computer. I usually do a zoom in of it, but I don't think I need to because the screen is so huge. See. So this whole thing is, roughly, millimeters wide. This whole kind of trap in here. And what's shown, you can see this kind of racetrack shape. And all of our qubits, they live right above the surface of that trap, along that racetrack. So they always live along the one-dimensional ring. And so our qubits are singly ionized deuterium atoms. And because they're ionized, they're easy to trap with electric potentials. And so we can take these qubits and we can shuttle them around above the surface of this trap by applying time-dependent voltages to all the little electrodes you see. Like every one of these little gold squares kind of surrounded by black is an independent electrode that we can control the voltage on. A couple of technical things, in order to keep them cold while we're moving them around, to keep their motion cold, it turns out you can't really cool them directly without destroying the quantum information in them, so you have to co-trap another ion. We use barium right now. And then, by cooling the barium, the light used for cooling doesn't touch the information in the qubits, but the barium kind of sympathetically keeps the deuterium cold enough to do high-fidelity gates. The qubit itself is stored in the ground-state electronic manifold. If this is stuff you know what this means. If not, it's not that important. The important thing is that this qubit has a very long coherence time. So the T1 time, the time to change between these states, for all intents and purposes, it's infinite. It's not really relevant to us. The T2 time, or the dephasing time of this qubit, is relevant, but it's relatively long. It's on the order of 10 seconds for us. Okay, I think it's helpful to see a little schematic of how a circuit actually looks like when run on a computer like this. So I have this video here. And so you can imagine the circuit on the left with qubits 1, 2, 3, red, green, blue. And the first thing that has to happen in this circuit is they have to be initialized. And as with all of the other quantum operations in our computer, this is done with laser adjustment. So the qubits will be initialized to the 0 state. And then in order to step forward in the circuit and apply single qubit gates, it's important that the qubits be located in these gray shaded regions, are specific gating zones in the trap where lasers are focused over in order to do the quantum gates. And then if you then look forward in the circuit and see that you need to gate qubits 1 and 2, they need to be next to each other. So in general, these separations here shown on the screen are kind of hundreds of microns. To bring them close and actually do 2 qubit gates, we need them to be in the same kind of harmonic trapping potential, only a couple of microns apart. And so we can do that by shuttling qubit 2 over to qubit 1, putting them in the same trapping potential, and then sweeping all the details under the rug. We do laser-based gates in order to say implement a C0 gate. And then you would say, well, I want to gate qubit 1 and qubit 3. It doesn't really look possible in this configuration because qubit 2 is in the way, because they live kind of in 1D, but we can swap them past each other. and bring them over into a configuration where they then can be close enough together to do 2 qubit gates. So now we bring them into the same trap, and now we can execute this gate on qubits 2 and 3. And then similarly, we want to measure, say, qubit 2 in this setting, kind of drawn it conveniently in a way where qubit 2 is already sitting all on its own, so we can just measure it. It turns out it's actually pretty important that these length scales are very large, because we can address qubit 2 with a laser and measure it in a way that's very non-destructive to the other qubits because it's so far away from them. And I'll talk about that a little more. It's pretty important for the work that I'll show in the rest of the talk. Okay, let's see. So I'll wrap up the talk about the details of the hardware with just an overview of some of the fidelities achieved. And I'll just kind of highlight the most important things to keep in mind, especially in the context of the work that I'll show you. So the first, with one exception that's not too important, the biggest number on this slide is this 18. So this is 18 10 to the minus 4, or about 2 times 10 to the minus 3. From randomized benchmarking, that's the fidelity measured for our native gate. And our native gate is up to single qubit rotations. It's equivalent to a CNOT gate. So that's sort of the thing we can implement easily. And actually that number on the H1 device that this work was done on is even a little bit closer to 1 times 10 to the minus 3 at this point. But this number is for this larger H2 device. And I don't know if I said it, I should have. So this H2 quantum computer that I showed a picture of, it's initially designed to hold 32 qubits. That's sort of the way we've initially brought it online. But the actual design of the architecture in the trap had in mind holding many more qubits. So it will be upgraded over time to have more qubits. Okay, another important thing on this slide is what we call the fidelity of parametrized 2 qubit gates. And so if you look at a gate like this, if you wanted to implement a partial entangler, so if theta here were pi over 2, this thing would be kind of a control phase gate more or less. It'd be a perfect entangler. It's not probably surprising to anybody here that for many quantum simulation purposes, it's nice to have gates that can have parameterized angles. And nominally, if you wanted to do that just using perfect entanglers, it would require 2 2-qubit gates per one application of this. So your error for a weaker entangler would actually be twice as bad as the error for a perfect entangler. But one nice feature of this platform is that we're actually able to implement these kind of partial entanglers natively, and in general with fidelity that improves as the angle goes down. So the more weakly entangling the gates are, the better the fidelity actually is. And that's what's being shown in this plot here. You can see that for the perfect entangler out at the right, the error is about 2 times 10 to the minus 3, like what was shown up here, and then it continues to go down as you make the gates more weakly entangled. Okay, the last thing I wanted to highlight is what we call measurement and reset crosstalk. So this is a pretty important metric, right? Because in the future, what we'd all like to be doing is quantum error correction, where you need to be doing receiver measurements in the middle of the circuit, and ideally measuring ancillas in a way that's non-destructive to the other, the data qubits that you don't intend to measure. And so what I mean by crosstalk here is when I go in and try to measure 1 qubit, with what probability do I accidentally measure some other qubits that I didn't intend to? Same thing for reset crosstalk, just when I reset a qubit. And so that's kind of drawn up here. And one way of thinking about these numbers is that essentially if I have 2 qubits and I go in and I measure one of them, the probability with which I, by accident, extract information from the other or measure it is less than 1 in 100,000. So it's really low levels of crosstalk, and that's really afforded by these large separations between the ions when we do quantum operations. Okay. So life's not all good with trapped ions. This architecture is very nice from the standpoint of getting low crosstalk and high fidelity. The price you pay for keeping things very far apart to drive that crosstalk down is primarily in runtime. Right? You have to move these ions around between those places, and that sets some speed limits on how fast the computer can operate. And so for us, the typical time it takes to implement a layer of 2 qubit gates in a kind of dense circuit of gates is about 50 milliseconds, so it's relatively long. It's still short enough compared to the coherence time that memory errors during these 50 milliseconds are relatively negligible, but nevertheless, it's a time that you have to incur to run a circuit. Okay, so I'm going to focus in on this sort of capability of doing mid-circuit measurement and reset with low crosstalk. And while the applications of that to quantum error correction are very well known, I'm going to focus on a different, more near-term aspect of this capability toward quantum simulation. And I'll give just kind of a highlight reel of some things that have happened, roughly over the last year using this kind of capability before really zooming in and talking in much more detail about the one on the right over here. But Ellie, who's here, Ellie Cherkov was responsible for this work that I'm showing over here, where by making kind of controlled injections of these resets, which can drain entropy out of the system, setting a qubit from 1 to 0 removes entropy from the state in some sense, or it can. You can arrange to have circuits where even after many, many, many gates in steady state at very long times, you can have a phase transition depending on the rate at which you inject those resets. If you say inject them to some probability at every step of the circuit, as a function of that probability, you can have a phase transition. And this is some really nice work that actually showed that, contrary to what was believed in some literature that's out there, a transition of this nature seemed to have, from measurements on the quantum computer along with a bunch of assisting classical calculations, seemed to have classical critical exponents. But I think the cool thing is that we can actually implement these kind of non-equilibrium models with sufficient fidelity to go in and really see what the critical behavior of the associated phase transitions is. Another line of work that's made possible by this is something that we've already heard a little bit about preparing topological states of order. There's been a few papers recently I'd encourage you to look at if you're interested, but I won't really talk about any of this, other than to say that it's been known for some time, and now we're sort of in an era where we can actually put this into practice, that you can prepare many non-trivial topological states in relatively low depth, lower depth than you could unitarily, by using measurement and then feedback, classical feedback, quantum feedback based on classical processing of the neural. The work that I'll actually talk about is, shown over here. So it's going to be about utilization of this mid-circuit measurement and reset as a tool for implementing one type of what I'll call a quantum tensor network. So this work will be about a Mera tensor network. And I don't even really intend to give like a clear definition of what a quantum tensor network is, but I'll try my best to just motivate loosely speaking what I'm talking about. And so if you think about classical tensor network techniques, one way of thinking about the insights that people have gained from them and the reason that they're powerful is that if you take a state of n qubits that actually emerges in nature, say as the ground state of some Hamiltonian, naively you would expect that the classical resources required to even just express that state, just based on the memory requirements, would scale exponentially the number of qubits. And the real lesson of tensor networks over the last couple of decades has been that that's really not true, right? In general, the actual kind of cost is exponential in the kind of entanglement entropy of the worst case, bipartition of the system, which for typical states is much less than the total number of qubits. So the cost may still be exponential in something large, the entanglement entropy, but it can be exponential in something much smaller than the total qubit number. So that's what classical tensor networks can get you. You can think of quantum tensor networks as a general attempt to answer the question of how can you take that benefit and convert it back to now doing a quantum simulation that instead of using n qubits encodes a state with less than maximum entanglement on n qubits using only a number of qubits proportional to the entanglement entropy. So it maybe sounds reasonable that that should be possible. And it turns out that by porting many tensor network techniques onto sort of language quantum circuits, you can actually do that. And this will be one demonstration of how that works. Okay. So the key kind of idea of how that compression is possible, how you can represent the state of, say, n qubits on fewer than n qubits. And at face value, it maybe sounds a little silly that you could do that. But here's a very simple example of how you can represent kind of the output of a circuit on 3 qubits using a circuit on just 2 qubits. And this is really the building block of any quantum tensor network kind of implementation. So take this circuit here, and first thing you'll notice is that if you want to measure the first qubit, M1, you can look back in time and ask what gates and what input qubits actually influence that outcome, right? And it's not all of the inputs, because qubit 3 can only kind of have an influence that forward propagates through this gate and impacts either the second or the third measurement, right? It can't impact the first gate. So to measure qubit 1, oops, sorry, I wanted to draw something first. To measure qubit 1, all you have to do is implement the past causal cone of the circuit. So all the things in the past that influence that output, which in this case is just 2 qubits. So you could run just this part of the circuit, which is the same thing shown down here, just acting on 2 qubits. You can measure qubit 1, and do the same thing in this 2 qubit circuit. And now notice that in principle, you could do this measurement earlier in time than you do this gate. Then you could take this measured qubit, you could reset it into the state psi 3, and inject it into this C0 gate as the target of this C0 gate down here. And down in this circuit, that's exactly what's being shown. This measured qubit 1 is being now reset to the state psi 3 and injected as the target of the C0 gate between qubit 2 and qubit 3 prior to measuring 2 and 3 now on a 2 qubit system. So the statement is not that these circuits are truly equivalent, right? They can't be. The circuit on the top produces a state of 3 qubits prior to the measurement. That state never exists down here in the circuit. The statement is just that they're kind of isomorphic in the very specific sense that they truly sample these measurements from identical distributions, right? So the outcomes of these 2 circuits will be indistinguishable from like any classical post-processing. So in that sense, they're really equivalent. Okay, so that's the key technique. I'll just go back now and remind you of why this kind of measurement reset crosstalk issue is important, which is that, in this circuit, when you measure qubit 1, it happens at the end of the circuit. So you could ask, what happens if there's a little crosstalk and I accidentally measure qubit 2 and 3? It makes sense that it won't really matter because you're trying to measure them anyway, right? So there's not a big issue if you have crosstalk in this situation. But if you move the measurement earlier in time into this circuit, and now you have some crosstalk where you accidentally measure this qubit down here, that error is going to get propagated to this gate and screw up these outcomes, right? So the equivalence of these 2 circuits is only true if this measurement is truly ideal in the sense that you don't accidentally measure any other qubits in the circuit. So this low crosstalk is really responsible for the ability to make this equivalence and do this kind of qubit compression. Okay. So I'm going to show how you can use those kind of ideas to express a state that I'll refer to as a MERA, so it's called multi-scale entanglement renormalization ansatz. If you're not familiar with it, the details are honestly not all that important. The idea of these kind of tensor networks goes back quite a long ways, originating with Vidal. But it's maybe not so surprising. These things look a little bit tree-like, where you can picture them as, ingesting, say, qubits at the center of this tensor network. And then they kind of flow in a circuit-like fashion along these lines to the output. And it has the structure of kind of a tree, where as you move out, a distance r, you're always kind of increasing the number of qubits by a fixed scale, like a fixed multiplicative scale. And that structure lends itself very well to expressing states at the boundary of this tensor network that are scale invariant. And so another way of saying that is it's a very good ansatz for states that are critical states, or ground states of the Hamiltonian or Hamiltonians undergoing phase transition. So it's very nice from that standpoint. I'd like to be clear up front what our goals are in trying to implement this on a quantum computer. It's already been, so the way that these ansatz are used classically is typically that you would just put some parameters in these tensors, and then you would optimize those parameters to try to reduce the energy of the state that comes out of the output. And once you got low enough, you would say, okay, this is my best guess for the ground state of the Hamiltonian that I care about. The quantum version of that, while not impossible, would be something like EQE. I think we've already heard some opinions about the utility of EQE. The only thing I would add to it is that if you're working with a computer as slow as this one, it's even worse than anybody was alluding to yesterday. So we don't do it, we don't even try. The optimization of these tensors is all done on a classical computer. Actually, I would maybe make one comment about EQE in general, which is that I think this barren plateau problem is not actually so obvious that it's a completely generic problem. And while VQE is not a great idea on hardware that's particularly slow, I think in some sense there's probably a lot to learn from the classical tensor network community about how to avoid these barren plateaus. Ansatz is based on the knowledge already learned from tensor networks. Could be very useful in making VQE a sort of more promising type of algorithm. And there's a lot of nice work to that extent in the literature, but it's something worth keeping in mind. One way of saying this is at face value. I think if you looked at the DMRG algorithm, which has basically been responsible for solving all 1D systems, if you just made a barren plateau argument, you would think that it wouldn't work, right? but it turns out it's the most powerful technique we have, and it's an incredibly stable and well-controlled numerical method. Okay, we do all the optimization on a classical computer. The goal here is just to show that given in hand the tensor network that's been optimized to have a low energy with respect to a particular model, can we then represent it accurately enough on a quantum computer to extract the correct critical properties of that model from this ansatz? So that's what we're trying to do. Let's see. The first kind of simplification that you get when trying to implement a network like this, is that if you only want to measure sort of a k-local correlation function, say something like the product of Pauli operators over here and over here at distance j minus k apart. So in condensed matter, we would say a correlation function. Then you actually only need to implement a small part of this tensor network. You have to look only at the past causal cone of the network, and you can really forget about everything outside of it. So the relevant kind of tensors are just shown here, colored. Everything else has now been grayed out. And the key thing that makes Mera a good tool classically is that the width of this causal cone as you go from the boundary into the bulk of the tensor network actually stays constant, and that means that the overhead of contracting a tensor network like this classically does not scale badly with the number of qubits that you have in the ansatz. It really just scales with the width of this causal cone and with a parameter called the bond dimension, which really just controls how many degrees of freedom are encoded in each of these lines in the tensor network, and it's what endows the tensor network with its expressivity. So this bond dimension, the cost of contraction in 1D scales, polynomially, but not like a very pleasant polynomial. The bond dimension is something, depending on how you do it, it's something like pi to the 8th, something like pi to the 16th, depending on how you do these contractions for 2D networks. So right away you can say, okay, for large bond dimension, these things are maybe efficient classically, but not particularly fun to contract, right? So I think there are some opportunities there, even for just kind of polynomial improvements in contracting these things on quantum computers, given the very high polynomial costs here. I think many things that we would like to do, in addition just to pushing up a high bond dimension and hopefully getting around some of these costs, there are generalizations known for Mera, called Mera, that effectively map very nicely to qubits and reproduce very large bond dimensions and can greatly increase the expressive power of these networks. It'd be a very nice thing to implement at scale. Also, appending time evolution to a Mera, if you want to study some dynamical properties of a critical system or system near its critical point, is the thing that's, again, hard to do classically. In principle, and I'll mention this a little at the end for time evolution, this is all stuff that can be done with exponentially fewer resources on a quantum computer than a classical computer. And the asterisk is because I know there are people who will probably give me a hard time about exponentially less here, that you're welcome to give me a hard time afterward if you want. There's some justification. Okay, so the model that we chose, because what else would you choose as the first model, is the transverse field-Ising model. You have a Hamiltonian that's the sum of nearest neighbor interactions. It's written a little funny. They're usually written along the z direction. Here they're going to be along the x direction. So this part of the Hamiltonian, and I should have put a minus sign between it, it prefers all the qubits to be aligned along plus x or along minus x. And then you add to it a transverse field, which in this case points in the z direction and wants to disorder the system. So it wants to kind of break that spontaneous ordering into plus or minus x. And this Hamiltonian undergoes a very well understood phase transition at lambda equals 1, at which point the ground state of the model becomes scale invariant. And if you look at the decay of correlation functions of the order parameters, so the polarization along x, what you find is that it decays in space like a power law, consistent with that scale invariance, and the critical exponent for that power law decay is well known to be a quarter law. Okay, so when I talk about implementing this ansatz accurately enough to measure the critical properties, what I really mean is we're going to take this Mera, we're going to put it on a quantum computer as a circuit, and then we're going to go in, we're actually going to measure this correlation function decay, and we're going to see what answer we get, whether we can observe or resolve the correct critical properties. And so there's a bit of a song and a dance to how you do this. If you look at this tensor network and kind of zoom in on a section of it, you'll see some things that look like gates, like these square ones, right? They ingest kind of 2 lines and put 2 lines out. And then you'll see some things that don't look like gates, like what the hell is something that ingests 1 qubit and outputs 2 qubits? But such a thing, if it's an isometry, technical term for it, it can always be embedded in a unitary with a fixed input state, right? So all of these kind of free-legged tensors in a Mera can be turned into gates with just fixed input states. And in general, I talked about this, you might think of this as a 2 cubic gate if the bond dimension is 2, but if, chi is the number of indices that this leg kind of runs over the tensor, then you need a chi dimensional Hilbert space, or say log 2 of chi qubits coming in along each of the legs here. And for us, we did this implementation with chi equals 4, which means you just need to decompose each of these legs into 2 qubits to get chi equals 4. And so we do that in a not completely general, but sort of motivated way with this kind of brick wall style ansatz, where now, this entire isometry was first decomposed into a unitary of, ingesting 2 kind of 4-dimensional legs, further decomposed into ingesting 4 qubits, okay? And we do this for all the tensors in the network, and then each of these little things is now just a proper 2 cubic gate, which we then parameterize as native rotations with these kind of variable angle gates that we have, and a bunch of single cubic gates. So we do this in a way that is sort of reasonably smart and respects the symmetry of the model. Let's see, like 1 minute is okay? Okay, I'll try to wrap up pretty quickly. So the few points I want to make here are really just, where the capabilities that we have in this kind of architecture come in when actually trying to implement this. And I'll skip over a couple and just make a point of most prominent. The first is that if you look at these optimized tensor networks, they often have pretty small gate angles. And you can look at the distribution of gate angles in that circuit I showed you and see that it's very peaky around 0 angles. So the fact that we have improving fidelity at a smaller gate angle is actually a big benefit for implementing networks like that. The other thing is the way that this qubit reuse comes in is if you look at how many qubits you need to implement this, one way to think about it is just go count isometries, right? Because every isometry ingests a new pair of qubits for bond dimension 4. So you think it's just 2 times the number of circles in this diagram. But actually, what you find is that these qubits exit the causal cone of the circuit, so these lines that just leave, never to return, they go out just as often as new isometries are introduced. So as long as you can take those qubits, reset them, and re-inject them as new qubits to make new isometries, you actually only need a constant number of qubits if you have the circuit measurement qubit reuse to implement this entire circuit. And so with actually 20 qubits at the most, we're able to represent 128 qubit state at the boundary of this mirror. And then, without talking at all about any of the error mitigation techniques that are applied, I'll just wrap up by saying, if you go in and just take the data and measure the correlation functions by implementing now, for the same merit, different circuits now corresponding to different distances along the boundary state, and measure the correlation function decay, and fit it, you get, a relatively nice answer, so you can get a very good quantitative agreement with the correct critical exponents for that state. I think, instead of explaining this, I'll just say that one promising outlook for this is that you can append time evolution to a MERA in a way that classically would come at kind of exponential cost, it's like multiplicative exponential cost in memory and interactions. Exponential in the time of the evolution that you're appending to the circuit. We know that quantumly you can do this at a cost that's just linear number of qubits. So I think this would be a really nice way to not push this calculation that admittedly can be done entirely classically. We did it classically in order to optimize the MERA. You can then take that as the starting point for a dynamic simulation, inject it with a faithful representation of a critical states, and do it in a way that's efficient. Okay, I'll wrap it up.
It's time to speak. We have time for maybe 1 or 2 questions. I wanted to ask something. In the slide 24, we showed that in order to calculate the correlation, you don't need to explore the whole space, you only need to take into account a small region, okay? Is there any way to anticipate a priori which region you will be able to consider, or you have to explore this region?
So you're saying which part of the MERA has to be kept in order
to
Oh yeah, so there would be efficient classical ways for determining what part of the network has to be
a priori, it's not that
Yeah, priori, yeah.
Okay,
Yeah.
thank you.
Yes.
More questions?
Yeah, that's a great question. I think one thing I would say is that, one reason we focused on critical states is that they're probably the hardest place to do adiabatic state preparation. Maybe not the hardest, but, harder than for gap states. So this is a nice way of kind of getting around that and just trying to directly find through variational optimization a good representation of the state of the circuit. But I won't claim that it's the best way. I don't know that that's true. So I don't really know the answer to your question.
Yeah, so, I mean, you mentioned you have this isometry constraint. Can you just say how restricted that is for, that constraint doesn't exist in classical computers?
Yeah, so it is somewhat restrictive. I mean, I would say that tensor networks that are built out of isometric tensors, if they have the right structure, can be converted into quantum circuits. I mean, one way of thinking about how restrictive the isometry constraint is that if you don't have it, say in a 2D tensor network like a PEPS, you know that contracting it should be something that's harder than what a quantum computer can do, right? So from the standpoint of kind of computational complexity, removing that isometry constraint has pretty profound implications.
All right, let's again.